Hey, we've already seen how to use definite integrals to compute the area under a curve, meaning the area between a curve and the x-axis. Today we're going to take a look at how to compute the area between two curves. Here we have two curves, f and g, and 2 points on the x-axis that we'll call a and b. And what we're looking to compute is the area between these two curves from a to b, the shaded area here. Well, we already know how to compute the area under the curve f from a to b and above the x-axis. That's the integral from a to b of f of x with respect to x. And we also know how to compute the area under the curve g and above the x-axis between a and b. That's the integral from a to b of g of x with respect to x. And the basic idea is that the area we're looking for, the area between the curves f and g, is the area under the curve f minus the area under the curve g, which is the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And we can simplify that a little bit using the properties of definite integrals. That's just the integral from a to b of f of x minus g of x with respect to x, or in other words, the integral of the top curve minus the bottom curve. Okay, let's do an example. We'll look at the area between the curve y equals e to the x and y equals x on the interval 0, 1. And by the formula we just came up with, this is the integral from 0 to 1 of the top curve minus the bottom curve, so e to the x minus x with respect to x. And that's an easy integral to compute. We get e to the x minus 1/2 x squared evaluated from 0 to 1. And when you work out the arithmetic, you get that the area between these two curves from 0 to 1 is e minus 3/2. Let's do one more. We'll look at the area between the curves y equals x squared and y equals x on the interval from 0 to 2. And this is more or less the only kind of trick you'll see in these area between two curves problems. As we go from 0 to 2, we need the top curve minus the bottom curve, but which curve is the top curve and which curve is the bottom curve changes at this point somewhere in the middle that I've marked with a black dot. And so the first thing you want to know is, where is that black dot? And you could probably guess that it's the point 1, 1, but for situations where you couldn't guess, it would be nice to have some technique to figure out what that point is. And that's the point where these two curves intersect, meaning where their x and y values are the same. And to figure out where that point is, we can simply set the equations of the curves equal to each other. When y equals x squared, y also has to be equal to x, and so x squared has to be equal to x. And that's a quadratic equation. It's easy to solve. You factor, and you find that the values of x that make it true are x equals 0 and x equals 1. X equals 1 is the one that we had guessed, and it's clear from the picture as well that the two curves also intersect at x equals 0. And so how do we find the area between these two curves? Well, from 0 to 1, y equals x is the top curve, and from 1 to 2, y equals x squared is the top curve. And so we need to break the area down into two parts and compute the area of the region between 0 and 1 and the area of the region between 1 and 2, and simply add them together. In other words, here is our expression for the area. It's the integral from 0 to 1 of the top curve minus the bottom curve, that's x minus x squared, added to the integral from 1 to 2 of the top curve minus the bottom curve, that's x squared minus x. And these are easy integrals. We get 1/2 x squared minus 1/3 x cubed evaluated from 0 to 1, plus 1/3 x cubed minus 1/2 x squared evaluated from 1 to 2. And there's a bunch of arithmetic to do, and you do it slowly and carefully, and in the end, you get the rather surprising result that the area between these two curves is precisely 1. Okay, that's how you compute the area between two curves. There is, of course, a homework assignment to give you some practice. Have some fun with it. Looking forward to seeing you in class.